So this is the agenda and structure of my talk I wanted to cover today. First, I will describe briefly Solexel and our value proposition. Then I think it'll be very helpful to give you an overview of crystalline silicon PV technology landscape and a little bit of overall PV market data. Our focus is thin silicon, and really looking at crystalline silicon, you can call it ultra thin because we are operating below 50 microns of crystalline silicon absorber. So I'm going to explain the motivation behind using thin crystalline silicon as it relates to high cell and module efficiency. Then we will do a little bit more of a deep dive into Solexel's disruptive technology and our progress at the company, and then I will leave you with some takeaways and a conclusion. So a little bit of overview on Solexel. I started the company over 6 years ago, and then incorporated and closed the Series A financing in the first part of 2007. The Series A financing was led by Kleiner Perkins. Professor Saraswat has been involved from very early days as a special advisor. We do have a fully operational pilot fab. It's a pilot engineering transitioning to production fab in Milpitas, along with a complete test and reliability engineering test lab. So our technology platform is very IP rich, and we do have a portfolio of over 170 inventions. They are primarily mostly in-house patents. We have also licensed portfolio from some key institutions. Besides the venture financing, we have received $17 million of R&D grants, mostly from DOE, Department of Energy. Actually, the last of these we received less than a year ago from DOE as part of the Sunshot program. It's a $12.9 million program based on which we are applying our technology, high-efficiency technology, to building integrated photovoltaics, rooftop shingles, working with our partner Owens Corning. We have also received a significant incentive package from government of Malaysia to set up mass production lines there. So far, we have raised $150 million in 3 rounds, Series A, $50 million, followed by Series B, $98 million, and our Series C is in progress. We are about 2/3 of the way through. And the proceeds from Series C we are using towards demonstration of the high volume manufacturability of our technology on the copy exact high volume manufacturing tool set. So Solexel, our technology actually has a unique attribute. We essentially eliminate the performance versus cost trade-off that has been governing and constraining the mainstream traditional PV technologies. On one end of the spectrum, you have the thin film leader First Solar with cadmium telluride technology, relatively modest module efficiency today, around 12.7%, and at least up until recently, the lowest cost in terms of module cost, manufacturing cost per watt, at about 72 cents per watt this year. Efficiency is relatively modest, so really the ASP with that level of efficiency, you don't command any premium. On the other end of the spectrum, We have a company like SunPower, the provider of high-performance modules with industry-leading efficiencies today at a little bit over 20%, and by next year actually moving to their higher efficiency, 21.2% panel efficiency. But at a manufacturing cost, which is you could say significantly higher on a per watt basis than the best of thin film. On the other hand, a company like SunPower has been able to command premium on their pricing, so the ASP compared with thin film is much higher, and that is because each percentage absolute efficiency point has a value of 5 to 7 cents per watt at the installed system level. So basically, let's say a 7-point or 8-point efficiency advantage there at the installed system level at the minimum has a value of 40 cents per watt. So you can actually take some of that as a pricing premium. So what, and then you have the main crystalline silicon population, which is somewhere here, and I'll get a little bit more into that. What we do at Solexel, we really have a platform technology that enables us to combine the best of both worlds. So we, our architecture enables us to operate in the essentially elite high-performance group in terms of efficiency, like SunPower, but at a cost as we scale that is actually significantly below the best of thin film, in this case, First Solar. And really some of the very important attributes are always efficiency, manufacturing costs, energy yield, and I'll get into some of the other very interesting attributes for our technology later on. So almost 90% of the crystalline 90% of the PV market is served with crystalline silicon PV, and essentially majority of the manufacturers go through the same macro flow and supply chain as I've shown here. So you start with purified silicon source gas, typically trichlorosilane or silane, and then from that you manufacture polysilicon. From polysilicon, either monocrystalline ingots with Czochralski or multicrystalline silicon with casting technology, and then those are sliced into wafers using wire saw. You have to remove the wire saw damage and then make the cell. The cells are assembled into modules, and the modules are ready to be installed in the field. So looking at the industry costs, essentially today, the leaders, tier 1 manufacturers, the modules now cost a little bit over 70 cents, 72 cents per watt to manufacture. And at the installed system level, that today enables an installed system cost, which is a little bit below $1.60 per watt. Now, if you take the existing way of making the cells and modules, you're going to be essentially limited by the cost of materials at the cell and module level. Without introduction of any disruptive features, then you can have a floor on the cost that might be somewhere in the range of 60 cents per watt, and that would enable maybe a reduction on the order of another 35 cents per watt, going down to $1.25 with the mainstream technology. So if you look at this flow, these three steps, polysilicon, ingot, and wafering, actually are the most costly and energy-intensive steps. They account for almost 40% of the module manufacturing cost. And what we do at Solexel, we actually address, besides the cell architectural innovation that I'll briefly describe, we also address these three steps. We eliminate these three steps, and we replace that with a direct gas phase thin silicon growth. And this actually, in effect, makes us independent of the traditional silicon supply chain. The input to our factory is purified chlorosilane. We actually substantially reduce the net amount of silicon that is consumed in our cells by at least a factor of 10. Significantly lower, 2 to 3x lower capex. If you compare that to the same value chain for the mainstream crystalline silicon, less energy usage. It actually enables us to take the energy payback time in most installations to well below a year and make it comparable to the best of thin film. And essentially, it enables us, as we establish scale, to achieve actually an installed system cost of 80 cents per watt. This is because we have a clear path to a module manufacturing cost with this technology at around 40 cents per watt at scale. So the balance of system cost includes everything. Typically, what I'm showing here, it also sometimes you separate inverter from balance of system installation. In this case, this is for large-scale commercial installation. It includes everything. So I'll get into that because one of the key factors there is high efficiency, and the other part is that we actually not only can make our cells in standard glass covered modules, but very lightweight flex modules that don't have glass. And actually, this significantly reduces the balance of system cost as well. So let me move on to give you an overview of crystalline silicon PV technology, a little bit of update on the overall PV market as well. So if you look at the global PV demand, this is looking both at the actuals and also historical actuals and also forecasts. The PV market has been growing and is projected to grow at essentially a compound annual growth rate of about 40%. Now, you cannot find very many technology in the technology sector, very many sectors growing at this healthy rate. This is a growth in terms of gigawatts of demand. This is actually despite the challenging conditions in the industry since 2009. And if you look at the size of the market this year, it's projected to be around 30 gigawatts, and over the next 4 years, again, projection is that it will be essentially almost doubled. One of the interesting observations also here is that you see that the market demand is transitioning from a Europe-dominated market to a market that is more globally, where demand is more globally distributed. So another way to look at this is look at the cumulative global installed base of PV, everything, crystalline silicon and thin film. A key milestone that is forecast to be achieved this year is that the global installed base is going to reach about 100 gigawatts. And if you look at the really portion of market share of thin film, it's a fairly small fraction of the overall installed base, less than 15%, and at least it's not projected that anytime soon thin film, non-crystalline thin film technologies are going to challenge crystalline silicon type technologies. So when I say thin film, typically thin film means refers to anything, although we are strictly thin film, but we are categorized as thin film crystalline. I'll get into that a little bit more. But thin film is really CdTe, SiGs, amorphous silicon, organic PV, essentially crystalline semiconductor category. And really, you know, the installed base reaching about 100 gigawatt globally this year. If you look at the PV opportunity, it is truly a multi-terawatt opportunity. And I believe at least when we look at the 2, 3, 4 decades ahead, at least a 10 terawatt opportunity. So this really represents, in my view, you know, basically 1% of what could be the market opportunity for PV capacity globally. So really another interesting trend to look at is the progression of cost in crystalline silicon PV. You know, any companies that started back in 2006, 2005, 2007 with the assumption that, you know, polysilicon will be $50, $100, $200 per kilogram, you know, a lot of them are not around today. So just looking at just the last 4 years, if you look at the cost of, compared to the spot prices today, if you look at the cost of polysilicon, it has dropped by a factor of 20. And the cost of wafers has dropped by a factor of 10. So, you know, today you can buy full-size 156 format wafers around $1 you know, cost. And these used to be just barely 4 years ago, were over $10 per wafer. So the spot prices for modules are below 70 cents per watt. In many cases, actually, these are below the actual cost. Maybe they represent cash cost. So, this has been really great for acceleration of PV cost reduction and grid parity. Of course, it has also caused a lot of pain, particularly in the last 3 years in the industry. But overall, it's a great acceleration for the industry. So this is also an interesting trend of the module and installed system cost and the module cost. The installed system cost, essentially the total installed system cost represents the module cost, again, for commercial scale installations, and the balance of system cost. Now, if you have higher efficiency, the balance of system cost goes down. If you have you know, lightweight, flexible modules that you know, require less mounting hardware, et cetera, the balance of system cost goes down. So one of the really interesting milestones being essentially reached this year is that you see that historically thin film, or primarily First Solar CdTe modules, has been lower cost in terms of module costs and installed system costs than crystalline silicon. This year, actually, the trend has been reversed. So crystalline silicon module costs, the crystalline silicon module costs on the average is lower than thin film, the best of thin film, and the total installed system cost. And the trend in terms of installed system costs is expected to continue. So they both go down, but you're going to have the advantage in the case of crystalline silicon technologies. So let me switch gear from market now to technology. If you look at, and again, my focus is on crystalline silicon technology. If you look at the terrestrial solar irradiation, basically with silicon, and again, all the focus is on single junction silicon solar cells. When you have photon energy less than silicon band gap, essentially those photons don't make any contribution to your short circuit current or to internal quantum efficiency. The portion that really contributes is any photon energy above band gap, above 1.1 eV. Now, any excess photon energy above band gap gets thermalized. So really, the amount that can be effectively utilized and convert it to electricity is shown in green here, which is essentially the portion that has energy above band gap and also converted to electricity. So it's also good to know what some of the key measures and metrics are for crystalline silicon cells and modules. Many of these are actually same metrics are shared, almost all of them in the case of thin film modules. You hear a lot short circuit current or current density, open circuit voltage, and maximum power point, which is typically where you operate the panels at different times during the day. The product of maximum power point, current and voltage, is really your maximum power that you extract from the panel. And fill factor, which is also a very important parameter. When you multiply fill factor by short circuit current density and open circuit voltage, that's your panel or cell efficiency. Fill factor is a measure of ideality of your IV, so the squareness of the IV, and it's the ratio of your maximum power divided by product of short circuit current and open circuit voltage. Conversion efficiency, very important, the number one parameter in terms of importance in PV cells and modules. Another important factor also for energy yield is temperature coefficient. As you increase the temperature of the cells, which is typical in the field operation, how much power loss you have in your panels, the less the better. Normal operating cell temperature, the cooler the better, again in terms of energy yield. Internal and external quantum efficiency. This is really a measure of the fraction of either absorbed photons or incident photons that are converted to or contribute to electron hole pair generation and are converted to electricity. And last but not least is energy yield, very important metric for installations in the field. So short circuit current or short circuit current density is a very important parameter. It is, again, looking at single junction, it's directly dependent on the band gap of the semiconductor. Now, as you reduce the band gap of semiconductor, then more and more of the photons in the solar spectrum are available to generate electron hole pairs. So that's why, as you reduce the band gap, the short circuit current density max theoretical value increases. But on the other hand, actually, the trend is opposite for open circuit voltage and also fill factor. So now if you look at the, for instance, this is for germanium, silicon, and gallium arsenide, theoretical value for silicon, the maximum JSC, or short circuit current density, is about 46 milliamp per square centimeter. As I mentioned, VOC and fill factor have an opposite trend. So actually, when you go to a larger band gap semiconductor, those values increase. So you can expect that there is an optimum, or there is an optimum range for band gap that gives you the maximum efficiency. That's really predicted by the classical Shockley-Quasar efficiency limit. And you see that if you look at the maximum efficiency, this is essentially thermodynamic efficiency as a function of band gap. There is a maximum, about 33%. This really doesn't take into account some of the more practical limitations that I'll cover shortly. Basically, going to lower band gap, higher JSC, going to higher band gap, higher VOC, and typically also fill factor. And fortunately, actually, when you look at this, silicon and gallium arsenide, in terms of max theoretical efficiency, pretty much fall on the peak or near the peak efficiency capability. So that's good news for both silicon and gallium arsenide. Now, of course, the difference here is that silicon is an indirect band gap semiconductor, gallium arsenide is direct band gap semiconductor, so you can use much less gallium arsenide. In the case of silicon, you can make it very thin, but light management and light trapping becomes extremely important. So